Hello, my name is Bob D. Hilster, and I am your particle model guru. Today we're going to talk about the candle, but it's a series of 3 videos that I'm going to make. Today is the candle, the next one is going to be about the light bulb, and finally the third one, the hydroelectric dam. And yes, all of these are connected and have a theme to be presented. So let's talk about the candle. On the left side of this slide is the picture of a candle flame. And in that flame you can actually see different colors. At the bottom there's blue, then slightly above that there's orange and yellow, and then white, and then a little bit of yellow up at the top, and finally red. You could think of it as the colors of the rainbow coming out of the candle. Quite amazing. Then I found the explanation of the candle using these zones. There are 5 zones, and we're going to go through these 5 zones and explain what they are. But first, let's talk about how mainstream, how science out there explains how this candle emits light. In fact, this one is about how atoms emit light. And there are 3 steps. You can see there's a particle coming in at the upper left, and what they say, it excites the atom, and an electron jumps up to a higher level. Then it falls back and releases energy, and when it does that, it creates a photon. That's their explanation. By the way, you don't see anything about color there. The 3 steps are, they say specifically, a particle collides with and excites the atom. Now, that's an interesting thing. I'm not sure I ever saw an excited atom before, but that's what it does. The electron jumps to a higher level. It falls back, releasing energy in the form of the photon. That's the exact wording they use in that slide. So I ask the question, can energy create a photon? And how does that atom know what color to make? Well, energy to me is not real. If I can't find it in nature, it's not real. I can't buy a bottle of energy. I can buy a can of gasoline, but of itself it has no energy. It is just gasoline. Also, if it comes from math, it's not real. Nature does not know how to add, subtract, multiply, or divide. A particle, for example, may know its mass. It doesn't, but let's assume for the moment a particle knows its mass and it knows its velocity. But in order to know its momentum, it has to be able to multiply, and it can't multiply. Nature does not know about momentum. So I ask, how can a photon be made from nothing? Energy is force times distance. It's another mathematical statement. When a force, which is not real, moves an object of mass m at distance d, a photon is made. That's what I would have to be led to believe. That's their explanation. Yeah, obviously I'm not buying it. These are the zones of the candle, the flame. Zone 1 through zone 5. Zone 1 is the non-luminous zone. Zone 1 is this light blue area here, just above the dark blue. There's not enough oxygen for the fuel to burn. The temperature is around 600 degrees C. That's hot. And the temperature in each zone changes among different candles. So this is kind of a statistical average. Whoever made this information up made it this way. That's his idea. So it varies from candle to candle, but there's, in his opinion, this non-luminous zone, which means you can't see anything coming from it. Zone 2 is the blue zone. That's this dark blue zone at the bottom that you do see. And in that zone, there's plenty of oxygen, and the flame burns with blue light. And the temperature is around 800 degrees C, 200 degrees hotter. Zone 3 is this gray area in the middle. It's the dark zone. Pyrolysis, that is the cracking of the fuel, the fuel in this case is methane, begins due to a shortage of oxygen. This creates minute carbon particles, soot to be exact. The temperature here in this gray zone is 1,000 degrees C. The luminous zone, the part that makes the most light, where pyrolysis continues due to a shortage of oxygen, carbon particles continue to heat as they rise until they ignite and emit a full spectrum of light. We see it as yellow. The picture before videos, the actual photo was white, but nonetheless, a full spectrum of light. The temperature is around 1,200 degrees C. And finally, zone 5 is the veil. There is plenty of oxygen, so carbon particles burn more completely. The temperature is all the way up to 1,400 degrees C. And in the picture, you could actually see red. This information is taken from this link. Very interesting about that. So what we have in this from this information is that we can look at color versus temperature. Zone 2, blue at 800 degrees C. Zone 4, white or yellow at 1,200 degrees C. Zone 5, red at 1,400 degrees C. Does heat have something to do with color? So I looked up heat. And this is from Wikipedia, and it's talk about atom vibrations. Let's read this. The atoms and ions of a crystalline lattice, which are bonded with each other with considerable interatomic forces. By the way, in the particle model, that would be the G2 force field. These atoms and ions are not motionless due to the consistent vibration induced through thermal energy. They are permanently deviating from their equilibrium position. That is, if you look at atoms in a crystalline structure, they are sitting there vibrating due to the heat. Well, let's look a little bit more. What about absolute zero? Absolute zero occurs when all the objects stop. It's a crystalline form and they're not vibrating. You might reach absolute zero for a very short period of time, but it only takes one interaction with another particle or an object that comes in and hits and causes these things to vibrate. So you don't stay at absolute zero very long, or if at all, because there's always something coming around bombarding the object. So let's talk a little bit about solid, liquid, and gas. This to me is quite interesting, because as a crystalline object, the atoms stay basically in the same place and they vibrate. But as you heat it up, they vibrate more and more and more and more, and finally they can pass each other. And when they can pass by each other, you've got to turn it into liquid. And then you heat it up more and more and more and more, and finally the particle just flies away. And you have a gas. Solid ice turns to liquid water, which when heated turns to water vapor. You can take solid iron, heat it up, it turns to molten iron, heat it more, it can turn to iron vapor. That's how we get from solid to liquid to gas, through heat. So now let's look at vibration, wavelength, and color. Atoms with a small amount of heat have a very small vibration. The distance it travels back and forth is very small. Atoms with a large amount of heat travel further and the distance as it vibrates. Below, I made a chart of temperature, color for two zones as we see in the candle. I start with temperature. 800 degrees C temperature, and the other one is 1400. The vibration of the atoms at 800 for a candle, the methane particles that are vibrating, is a short vibration because the temperature is small for 1400. The vibration is long, creating the possibility of a short wavelength for light, and giving us blue color, which is what you get in this zone, or creating a long wavelength, which is red, which is what you get in that second zone. Now, at the time of combustion, the atoms are vibrating in all three directions, and you can see light coming from the candle in all three directions. The G1 particles are released depending on where they are at the time of combustion. If this atom is moving outward, away from the candle, then as those particles, as this atom would release this G1, and these particles would move out away from the candle at speed c, because these G1 orbitals are orbiting at speed c. When this atom moves inward towards the center of the candle, you have fewer particles. I didn't make the whole statement. When atoms move outward, there are many G1 particles that are pushed out. It's pushing out a lot out. When it moves inward, in that direction, the outward direction, it's hardly pushing any at all. When it moves outward, it's pushing a lot. When it moves inward, it's pushing very few. And that, to me, gives the possibility that the candle is, in fact, when the atom is moving outward, it pushes a lot. When it moves inward, it's not pushing so many out. It's pushing very few out, and then the atoms pushes out again, and it pushes a lot of particles. So you have a peak, a valley, and a peak. And it's very easy to visualize using the particle model that the candle is actually pushing out G1 particles at a rate like this. Well, and it's not going to be so nice and neat just like this is. David made this diagram, and these particles are placed based on the amplitude of this sine wave. And that's very clear. This sequence would give us a perfect sine wave. Nature is not that clean. It's messy. The clumps are probably different clumps, and the spacing between have fewer, but not always the same. But it really seems like the candle could be producing streams of particles in all directions, just like we have been proposing that the light is. A stream of particles moving at speed c with a repetitive pattern. Okay, I deviate a little bit here. David has recommended that I ask whether or not, if you like my videos, that maybe you should click on the red subscribe button that you'll find below the video that you're watching. When you do this, you'll get emails when I release a new video. Or if not, you can go to www.particle.guru, and you can look and select any or all of the videos that I have made. And if you do subscribe and you're now tired of getting emails, you can unsubscribe. So I recommend that you subscribe so that you will get notified of new videos being released. Now, normally I would go through this and very categorically explain what I just said and summarized. But I have to tell you, there are a number of times when I have worked on the particle model and looked into various aspects of things. It has become the highlight of my work with the particle model. I get very excited and get amazed at what I have learned by doing this. And this is true about the candle flame. I get very excited because when you look at the candle flame, you can see a rainbow of colors. And then I find this information about zones. This is information that's out there about zones, and it explains how the color of the flame is actually dependent on the temperature of the candle flame in those zones. And then you look at heat, and you realize that heat is vibrating atoms, and you put all this together, and all of a sudden you're starting to understand something about light and how the candle flame is producing light. It's amazing. It's a simple process. It's easy to understand, and it actually makes sense. It's logical. It's quite amazing. And all of that I present before ever saying anything about the particle model. And at the very end, to top it off, as far as I'm concerned, I add the particle model, and I can see clearly how the candle flame could be producing these streams of G1 particles making light. Get all excited, and I hope you're excited about this information as well. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I will explain more of the universe using the particle model. Thank you for your attention.